Hey, this is just a video to help people understand what an integral is because I feel like a lot of calculus teachers aren't exactly the best at teaching it. So this is kind of help you understand the concept of like area under a curve and how that relates to actually like integration. So to start off, here we have a displacement function. So this is s of x is equal to 5x squared plus 3x, and that's in meters. And so the question is, what is the change in distance or displacement from x equals 3 to x equals 5? So we can start off by saying, okay, we can just say, let's just plug in x for 5 and x for 3 and find the difference. And okay, so we got 86. So we know that the change in displacement is 86 meters. Okay, but let's say we have some velocity function, v of x equals 10x plus 3. We just want to find the change in displacement from x equals 3 to x equals 5. Okay, so we can use some integration techniques for this. And so you guys probably already know this, but you can just take the integral. And so this is just pretty straightforward. So we just take the end derivative of v of x generates s of x plus c, and then just find the change in displacement. All right. So first, we know our function is 10x plus 3. So we just do the power rule, do some math here, and then we get 5x squared plus 3x. And this is the same as the function up here. I'm doing that just so it's easy to comprehend. And so now we can just kind of find the change in displacement using the above methods. And so we just do 140 minus 54. We get 86. All right, that's great. Now, though, here's kind of where I try to explain what a Riemann sum is and how the area of the curve under a curve kind of relates to this. So what I have here is this visual representation of v of x equals 10x plus 3. And so graph looks like this, except I actually screwed it up. That's supposed to be up there to 3, but it's fine for this demonstration. And so then we can construct a new function from this called va1 of x. And so basically what this is, the a1 just means the interval, and a just means approximation too. And so basically, this looks like a left Riemann sum where you just have a rectangle start at the left side. So we start at 33, go to 4, right? And then go to 43, go to 5. It's just a straight line. But I want you guys to observe what happens to the derivative when we have it like this, right? Because I want you to observe that this is a straight line, right? And so that means that in the derivative world, that this is a line with a slope of 33 and a second line with a slope of 43. So you can go look at that over here, what I have. And so basically, we start at 3. So we're just going to start we can start anywhere because we're basically looking at the difference in height. But we're just going to start at 0 because that's easy to work with. And so we can start at 3, right? And then this line right here has a slope of 33, right? And it's on an interval of 1, so it goes up to 33 right here. And then next, we have our second line segment of when it goes to 4 to 5, and its slope is 43. So we go from 4 to 5, and then with a slope, that means we're going to go up to 76 meters, right? And so that this is kind of an approximation of the actual antiderivative. And so if you look right here, I have it written down, the actual answer is 86 meters for this question if we're trying to find the actual distance traveled. So that means that we're off by 11%. All right, so we're kind of close, but we could do a little better. But so to get better approximation, we can decrease our interval. So right here, I've constructed 2 more. Instead of an interval of 1, now it's an interval of 1/2. So you can see like VA of 1/2 of x right there. So that just means that we have more lines. But I want you to observe actually what happens in the derivative world when we do this, right? So let's take a look at this. So remember that the height of those lines, those previous lines, correlates to the slope here, right? And so the slope, it goes from 16.5 I don't remember the first slope, but it's on an interval of 0.5. You guys can just rewind the video. And then the second one's here. Then the third one we add, it goes 57. The fourth one, it goes all the way up to 81. Now this is an error rate of 5%. And actually, what I don't have written down here, but this, if you were to actually graph the antiderivative and move this up accordingly, because of course this is starting at 0, but we can start wherever, because we're just finding the height. But if you're to do that and you are to adjust this height accordingly so that this starting point actually starts on the derivative, then you'll actually observe that this line right here approximates that derivative better than this line right here, right? And also, what I want you to kind of think about is that if we instead had, let's say, 8 intervals, or an interval of 0.25, then this line would better approximate our actual derivative much better, and we would get a height, I don't know exactly, but more accurate than 81 meters, probably closer to 86 in some way. So yeah, I just want you guys to hopefully understand integration better. And like when you take a Riemann sum, that's actually kind of what you're doing. You're not, you can think of it as area under a curve, but it's much better to think of Riemann sum as a approximation function, because if you look at the derivative of that Riemann sum, you get a lot of line segments that slowly approach your actual derivative, and that is what a Riemann sum is calculating. So I hope that helps some of you guys understand what an integral is. Thank you for watching.